Okay, young physicists, today we are going to investigate the second of Kirchhoff's law, Kirchhoff's junction law for current. Now, previously you had investigated Kirchhoff's loop law for voltage, which is really just a consequence of the law of conservation of energy in a circuit. If you think about what a battery does, is it uses chemical reactions to raise the potential energy of a charge from low at one end of a battery to high at the other, and then it's just kind of like a ball or water flowing downhill. If you had 10 joules of energy at the positive terminal of the battery and you come down to the negative terminal of the battery, you must have lost that 10 joules or converted that 10 joules into kinetic energy, or the energy of the moving charge. So the loop law basically says battery raises us some voltage, and each loop we have to drop back down to that voltage, right? So in this case there's 3 loops. Today you're going to investigate a rule for current, and I think the current rule is actually a little bit more obvious than the rule for voltage. So here's what we're going to do. We're going to focus solely on the parallel circuit, and the first thing we need to do is we need to know, okay, it's called the junction law. What is a junction? Well, a junction, it says right here, is just a place in a circuit where current can split into multiple paths, so maybe like 1 and 2. If you look here, we got current coming in along path A, and it splits to B and C. Here we have current coming in C, and it splits to D and E. Or current can be where it is merging into fewer paths, right? So here we have D and E merging into F, B and F merging into G, and then there is no junction of the current through the battery. So those are the junctions, real simple things. Corners are not necessarily junctions, right? There's no way for current E here is not changing numbers of paths, right? So sometimes that could be confusing to students. That this wouldn't be a junction, that wouldn't be a junction. So our task is really simple. Our task is to measure the current before and after these junctions and find a relationship. So that's what this data table is all about. Junction 1, what's the current at A? It's right here. Junction B, what's the current, or junction 1, what's the current at B? And junction 1, what's the current at C? We're just going to fill those out. And I think the results will be somewhat obvious. So similar to yesterday's loop law, you're going to use your data in these tables and come up with your own loop law here. And the final aspect is do a little research on Kirchhoff's junction law for current and see if your findings agree with what Kirchhoff said. So real quick thing about using, how are we going to make these measurements? Well, let's look at the PhET simulation. Here is a real simple series circuit. You're going to replicate the one that's in the diagram. I said series, this is parallel, and let me show you the fastest way to make these current measurements. We're going to use an ammeter. We're going to actually use an ammeter that doesn't exist in real life for a DC circuit, but for a simulation it makes it simple. I'm simply going to put where I want to put it. So I would measure the current here going into this junction as 1.8 amps. Here's the current coming out along one path, and then you can measure it somewhere else. So we're going to use this little guy for our measurements, as simple as can be. All right, guys, get to work on this and submit it when you're done, and then Kirchhoff's laws are aspect 3 of the circuit unit. We'll review a little bit, and then I'll give you the aspect 3 assessment. Good luck.